Hello all, my name is Alex Abrilla, and I will be presenting my project on Khintchine type inequalities for discrete random variables. The majority of this work was done last summer in collaboration with and with much advisal from Professor Tomasz Koch, so many thanks to him. Okay, so some background in Khintchine type inequalities. The classical Khintchine inequality tells us that for n IID random signs and arbitrary coefficients in the real numbers, when we look at their sum, we have for sharp constants a and p depending only on p and independent of the number of terms. This bounds, so we can bound the pth moment of the sum between the second moments. And the sharp constants are for all p are due to Hagerup. Inequalities of this form in general are very useful in probability analysis, largely because of the comparisons they give us between arbitrary moments where p and q are different. In particular, one classical application of this result is in the proof of the Littlewood-Paley decomposition in harmonic analysis, which breaks a function into components which are themselves have some kind of localized frequency. Okay. So then our contribution comes by partially extending these results with sharp constants to a specific type of symmetric discrete random variable, which generalizes random signs. If we let L be an integer greater than 0 and x distributed on negative L to L, we prescribe some mass at 0, and then we let x be uniform on the rest, and this is the general format. So I present two results today. First, we consider the case when delta equals 0 and there's no mass at 0. Let x be a random variable described above, and L is described above, with no mass at 0. Then we know that for arbitrarily large sums and arbitrary coefficients, we have for p greater than or equal to 3 the following inequality. So this establishes an upper type of Khintchine bound, where this is the second moment of the sum. So how do we go about proving this? So first, we can compute this moment here by swapping the xi with Gaussians due to independence. Note that these have to have the same variance as the xi. And then we see that really the inequality we're trying to prove is some kind of comparison between sums of our random variables and then sums of Gaussians, which are much easier to handle and better studied in general. So by independence and induction, we consider inequalities of this form here, where via independence we hold maybe the first n-1 of these constant, and same for the Gaussians. And then we look at the behavior of just one of these random variables, where a represents the sum of the other n-1, and then b is the coefficient of x1 or g1. So we can rewrite this cleverly using homogeneity and symmetry, and this turns out to be a well-known function that's convex. And so then we prove the more general statement, where if we have some convex non-decreasing function on the positive orthant, then we have this type of inequality here. And so to prove this type of inequality, it suffices to prove it for approximating test functions of the form x minus a, where we take the max of 0 and x minus a for arbitrary positive a. And the way we did this is by finding a weaker bound, in fact, a weaker integral bound by computing these quantities more or less directly, which was true for L greater than or equal to 7, and then checking the rest of the results by hand. Okay, so also I think it's important to point out that our constant in this case is really the moment of a Gaussian. And this is sharp because if we set coefficients to be equal to the 1 over the square root of n and then apply the central limit theorem, we of course see that these sums will tend towards normal Gaussians, showing which will have norm exactly this, or moment exactly this. Okay, that concludes our first result. So now we consider the case where there is some mass at 0. It seems in general that there's some trade-off that occurs for when we put some mass at 0. Then in empirical testing, it seems to be suggested that there are more restrictions on L. So L seems to vary inversely with the amount of mass at 0. Okay. So with that heuristic being said, first, it's in order to discuss this idea of Schur convexity in the title, we must define the non-increasing rearrangement of x. So for a vector x and Rn, this is just defined as the sequence of terms which begin with the largest coefficient and then decrease in the intuitive way you might expect. And then we say that for vectors a and b and Rn, a majorizes b if for all partial sums of the non-increasing rearrangement of ai, we know that these are dominated by the partial sum of the non-increasing rearrangement of bi. I think actually this should say b majorizes a. Sorry about that. Okay. So then to provide some intuition, in general, we know that, let's assume that the coefficients sum to 1 and we're working in the positive orthant. Then we have that the uniform spread of coefficients is always majorized by some arbitrary element, which is in turn always majorized by some standard basis vector. And we have this nice geometric picture here where we see, okay, so if we're looking at the points majorized by the standard basis vectors, then these are precisely the points in the convex hull of the standard basis vectors. And really this generalizes where to arbitrary points. Okay. So now our claim. If we let there be some mass at 0 between 0.5, then taking n IID copies of the random variable described above, and setting their mass at 0 to be delta 0, and letting p greater than or equal to 3, then we aim to show that this function defined here, which is the expectation of the sum of these random variables, is Schur concave. And we say in general that a function is Schur convex if it respects the partial order provided by modularization. So if b is modularized, or a is modularized by b, then well, in the Schur concave case, we know that the output of the function on b is less than or equal to the output of the function on a. So some key ideas in this proof. We use Ostrowski's criterion, which tells us that a function is Schur convex if and only if when we evaluate the partial derivative of the function along one direction and compare it to the partial derivative in another direction, then the partial in the first direction is larger than the partial in the second direction if the term in the first direction is larger than the term in the second direction. This works out to be equivalent to this condition here for our expression above here, where S is of this form and W is the sum of the rest of them, where we take derivatives accordingly. And then inspired by the results I stated over here to the left, we prove this inequality using approximating functions of the form here, so some kind of test function, but slightly more complex, where we multiply by x and then have this x minus a plus term here. Okay. Once we have the inequality here, as we did to the left, we can extend it using linearity and density of these functions to all convex non-decreasing functions. Note that the inequality we're trying to prove is linear, so we can abuse that in this case. Okay, and then the way we check the inequality for functions of this form is straightforward but technical, and really it reduces to verifying this condition here that when we have an inequality of this form, the best constant we can achieve is d equals 1, which somehow in some way relates to the the condition here that the mass at 0 can be no larger than 1/2. Okay. Thank you for listening, and I guess I'll be ready for questions when the time comes.